allow the incoming particle interact strongly with the surface, but not among themselves. Otherwise, you would have more than one atom absorbed at the same site. Okay? So, 4 basic assumptions that Langmuir said, and I would like people to remember this, because this is the key, right? Qualitatively, this is the key how you get that. So once you got this assumption, you can then apply these assumptions to equation star, which is my fundamental equation. Remember, equation star is very simple, really. It's just surface density equal to the lifetime, surface lifetime, times the impinging rate. And you can expand this further into a more complex equation like this. So you basically set this, essentially like this. And you just modify this n equal to tau I, except you have to qualify this tau I. You say that, well, it's fine, but we are only concerned about empty site, because it only works for empty site because of this last assumption that I made. Langmuir made that you cannot have 2 atoms absorbed in the same site. So you have to only consider the empty site. And how do you consider empty site? You take n, which is the number of the atom, right, on the surface, divided by n naught. N naught is the available absorption site. So it's like the coverage already. So 1 minus your coverage, right, is what is the site left over for further absorption, So it's kind of like this whole bit, right, is kind of like n divided by m, right? So this is the empty site idea that you have to introduce into your fundamental equations. And then the rest is just algebra, and then you can just invert. You start from this equation, you just invert this, work out the coverage, which is number occupied site divided by number of available site, okay, and not. And you got an expression that look like this. It's just inverting this equation. And you define chi as tau I divided by n naught divided by p. I'm missing a p in the original notes, so that's a mistake. So add a p in here. And what you got, once you got this, if you define this term, you can rewrite this coverage into something that looked like the Langmuir isotherm before. You have pi p, which is the partial pressure, divided by 1 plus pi p, as before. So you can rewrite. So you can see how the fundamental kinetic equation relate to this Langmuir isotherm picture that we have. Right? The Langmuir isotherm picture, one more time, is that you go like this. Right? Remember, this is my beta, this is 0 to 1 coverage, and this is my p as you increase. You can plot chi's of p here, like that. No matter is the same, p just a constant. It looks like this. Okay. So hopefully, so all I want to get at is what Langmuir assumed. Okay, that's where the interesting chemistry is all about. These 4 assumptions that Langmuir assumed is a strong, basically in an upshot, is a strong chemi-absorption picture for chemistry to observe. That's why the Nobel committee said in his speech that said that Erwin Langmuir, the contribution for surface chemistry. So that's the first time surface chemistry was mentioned in scientific work. So he was the guy who gave us this Langmuir isotherm idea. So it is fundamental to all chemistry as the impact is significant. This understanding is significant. And it's a good description of absorption process where strong chemi-absorption is observed. And it doesn't quite work for Fizy-absorption. Okay? And so let me talk a little bit about this Fizy-absorption. I'm going to come back to this little picture called BET model, which is applied to Fizy-absorption. come back to this. Okay, so what we got is this just to reiterate from the Langmuir picture, you have these this light time, mean state time, versus this delta H resorption, between the two, how they connect to one another. You can plot these equilibrium absorption behavior once you got this picture, Langmuir isotherm. You can plot it in this way, right? So here's some picture that you can plot in various ways, but once again, the key thing is this absorption isotherm according to the Langmuir model the way we understand. But you can plot it in n as a function of p, at different temperature, and n as a function of t at constant p. These are different p, and log of p divided by inverse temperature. This sort of thing you can plot it in many different ways between the absorption density versus temperature, pressure, or inverse temperature for constant T or constant P. These are constant T from the P process. And they look all the same, or differently. They look like this, but the fundamental thing is this coverage versus partial pressure that we see. So, Langmuir model worked best for absorption state with large delta H of desorption or chemi-absorption, and not very good at physi-absorption. So how do you examine this physi-absorption picture? If you are looking at a model that explicitly relaxes one of the Langmuir model, right? So here you are saying that the Langmuir model have absorbate, so that can have coverage more than one. So you can see Langmuir model cannot have coverage more than one. Why? Well, look at this picture. It approaches isototically to coverage equal 1. Why is that? Well, because Langmuir assumed no two absorption, no two atom can occupy the same site. You cannot stack them. You cannot put more than one atom on the same site, and therefore you cannot have theta greater than 1. The maximum is 1. But of course, in physi-absorption, as in condensation of water, for example, you would have more than one, because you can stack you can have condensation, you can have multiple molecules absorb on top of each other. So the picture I have is something like this, right? You would have little pocket of film building up. So this whole idea is of course related to fringe growth in industry, how you stack these molecules together. And one of the guys who, there's three persons, Granier, Emmett, and Teller, often known as the BET, in 1840 or so, come up with this so-called BET model, right, for physi-absorption. And it's of interest to talk a little bit about it because what they said is that, okay, how do you describe, other than Langmuir? Langmuir just have a monolayer absorption, right? BET model, you have multiple layer, and the multiple layer, that doesn't have to be even. You can think of these BET as patches, little patches, and condensation and things like that. And how would you describe such a system? So BET, Teller et al. Decided, okay, in order to treat this mathematically, we have to sort of think of this as little region. Okay, so they carve up different regions. So here you have a region where you only have your patches in the region. So here you have only monolayer coverage. Here you have a double layer, and then here you have monolayer again, right? And then here you have single layer, and double layer, triple layer, and so forth. So he's breaking down his multiple, very complex system into monolayer, double layer, triple layer, quadruple layer type system like this, and then starting to look at them in turn, right? So he started coming up with patches that broke